There you go.
We're back on the air. Okay, are there any questions? So the last thing we were talking about was distribution functions and density functions. And let me write some stuff on the board here. What we saw was that we could say that the probability that a random variable lies between A and B, including the B but excluding the A, which in fact doesn't matter if the random variable is continuous. So I'm reviewing things now. We defined what's called the distribution function, capital F. The subscript refers to the name of the random variable, which we're calling x here. And the probability then that x lies in this region is the distribution function evaluated at B minus the distribution function evaluated at A. And this is true whether the random variable is discrete or continuous. Now, if the random variable happens to be discrete, then this, which represents this probability, is given by the sum of the probability that x takes the value t sub I. Remember, if it's discrete, if the random variable is discrete, what that means is that it takes values in a countable set, which we call t1, t2, and so forth. This is the probability that x takes the value t sub I, and you add those up over all values of I, such that t sub I lies between A and B. So that's the case in which x is discrete. Now, that's what we've been doing all along, except that we haven't been so formal about it, and we didn't need to define this as a difference of distribution functions. We simply took the probabilities over whatever set we were interested in and added them up. But now the question is, suppose the random variable is continuous. If it's continuous, then what I showed you last time, which is the essential point of the course now, is the probability the mass function does not exist, but we still have a distribution function. So in fact, we could make an analogy. We could define what's called a density function, and let the probabilities, instead of representing sums, we let it represent areas, which are essentially the same thing. We integrate this between A and B. And this then would be the case in which the random variable is continuous. So this is the new stuff here. And what this means is that if this integral is given by this difference, then we have the fundamental theorem of calculus. And this is where the calculus in the course comes in, so I'll write it here. Here's the fundamental theorem of calculus. Fundamental theorem of calculus. And what that says is that if I want to evaluate this integral, what I do is I find another function, which I'm calling big F, with the property that the function that I want to integrate is the derivative of this other function, which I denote by an uppercase f. So we have uppercase f for the distribution function, lowercase f for the so-called density function. And so if I define this thing right here, in other words, if I could find a function whose derivative is this, then this integral is given by the difference between the f evaluated at the upper limit and f evaluated at the lower limit, and that's exactly what this says. So what we have to do is we have to find this density function. In fact, we could make this argument by analogy. There are various ways to look at it. So here's a discrete case. So here is the probability mass function. So here's the probability that x is equal to t, and here's t. And here are the particular values that the random variable takes. So let's call them t1, t2, t3, t4, and so forth. They don't have to be evenly spaced. They don't have to be positive. Remember that if we have a discrete random variable, it's completely defined when you tell us what the values are the random variable takes and what the probability is that it takes those values. That's the probability mass function. So let's suppose for the sake of argument that we plot these things. So here is the probability that the random variable takes the value t1, and there's the probability for t2, and t3, and t4, and so forth. And of course, the only requirement here is that these probabilities all have to be non-negative, and their sum has to be 1. So if I wanted to find the probability of lying between A and B, let's say, maybe here's A, and here's B. So what I would do is I would simply add up the probabilities of all the values the random variable takes that lie between A and B. Let me put another one in here. So I'll call this one T3, and that one T4, and this one T5, and so on like that. Okay, now suppose the random variable is continuous. So now, according to our formula here, what we have is another function called a density function, indicated by little f. Here's t. And now, this is a continuous function, like that. Actually, it doesn't have to be, it's just some function. And we have the limits between A and B. And whereas here, we said that the probability that x lies between A and B is the sum of each of the probabilities that x takes every possible value that lies between A and B. So it's all I such that t sub I lies between A and B, which is exactly what I wrote on the board over here. So this just sums up these guys. In this particular case, I would be 2, 3, and 4. Okay, now over here, instead of summing, what we imagine we're doing is this. We imagine that at each value t, there's a, remember now, with the continuous random variable, you can take all values in a continuum. So here is a particular value, and we replace the value here, the height, by the area. So in other words, there's a little strip here whose width is f of t, little f of t, dt. So in effect, this represents, I'll just put an arrow here, this represents the probability that x takes the value t. Of course, that probability is 0, as we argued. But what I'm going to do is I'm making an analogy here in that I'm going to take these infinitesimal, these strips of infinitesimal width and say that since the probability of each point is 0, I'll take the probability as being the area under that strip, and then I will add up all of those 0 areas, so to speak, and the result is that I will get the area under this curve, and that will then be the probability. So in other words, now, instead of, let me write it like this. Now, instead of adding up the discrete countable probabilities, I'm going to add up an uncountably infinite number of probabilities. So I take the probability that the random variable takes a particular value t, which I call density function dt, and then I add that up as t runs between x equals a, between a and b. So this is a direct analogy. This thing here can be interpreted as the probability that x equals t, even though that's 0. But I have an uncountably infinite number of zeros, and I add them up. That is, I take the area under that curve, and that gives me the probability. And in either case, if we define capital F to be the function whose derivative is small f, then in either case, that's the same thing as capital F evaluated at b minus capital F evaluated at a. Okay, so I said the same thing here as here. So you can keep this picture in your mind. Instead of summing up discrete values, you're adding up continuous values. You're adding up over a continuum. So one viewpoint is that little f replaces this probability mass function, and little f is a function whose areas are probabilities. And if we define big F to be such that its derivative is little f, then the probability that the random variable lies in any interval is big F at the upper limit minus big F at the lower limit. That's the fundamental theorem of calculus. And if we interpret F to be the probability that X, remember what F is, in general, F of t, capital F of t, is the probability that X is less than or equal to t. So if we define this in every case for discrete or continuous, then this formula works whether we're talking about the discrete case or the continuous case. Now, in order for to have a probability mass function, what we must do is we must tell you the values a random variable takes, and the probability that it takes those values, those must all be non-negative probabilities, and they must add up to 1. In the case of a continuous random variable, what we need to tell you is we need to tell you the density function, which must be a function that is non-negative and whose total area is 1. Okay, so let me go back and rewrite this now. Now we have one example of a continuous random variable, and that's the so-called uniform, which is what we did in homework 0, although at that time you had no idea about its interpretation. Okay, so to put it another way, here's our essential formulas. Notice that we must have, let's do it this way. The distribution function of x evaluated at t is equal to the probability that x is less than or equal to t, which is the same thing as the probability that x lies between minus infinity and t, which is the distribution function of x evaluated at t minus the distribution function of x evaluated at minus infinity. That is, the distribution function here minus the distribution function there. But obviously, since this equals this, this implies that distribution function of x at minus infinity must be 0. And similarly, if we plugged in a plus infinity here, we would know that the distribution function of x at plus infinity must be 1. Okay, so I can rewrite now like this. I could say, here is my distribution function. Now, I'm not talking about the distribution function as I did over here in terms of A and B. What I'm talking about is I'm defining now what I mean by distribution function in more formal terms. So, this is the probability that x is less than or equal to t. So if the random variable is discrete, that means it's the sum of the probability that x equals t sub I, summed over all I, such that t sub I is less than or equal to t. That's a discrete case. And if it's continuous, then I define this as the integral of the density function of x evaluated at u du between minus infinity and t. That's a continuous case. Okay, now notice that over here I have written t as the independent variable. That t is this t. What this says is add up or take the area to the left of t. So in this case, what I have is I've got this curve which represents the density function, and here's a value t, and capital F of t is the area to the left of t. So this area is capital F of t, and the curve itself is lowercase f of u. And the reason I've called it u is I want to reserve the t, which is the limit here in the density function, for the argument here. And this is important because if you don't keep these things straight, then when you do things like convolutions, everything is going to get screwed up. So you have to remember, this is the dummy variable. Just like here, the name of the variable here is I. And I'm going to add this up over all values of I, such that this thing is less than that. And here, I'm adding up these strips over all values of u, such that u is less than that. So these things are a direct analogy. Okay, so this is sort of a review of what we did last time. And now let me do this, let me look at this particular case. So any questions about this? Now, the difficulty as far as the book is concerned is that these things are treated in separate sections of the book because the mathematical tools are different, but the concept is the same. So in fact, what I want to do now is, let's see, let me say where this is. This thing here, in fact, is on page 145. And this one, right here, is on page 219. So it makes logical sense that these would be presented together, but they're many pages apart. The reason being that first he does everything with respect to the discrete case, and then he goes to the continuous case because the mathematical details are different. Okay, so I'm not emphasizing the mathematical details because actually they're unimportant. And in fact, in a more advanced course, the mathematical details sort of converge in the sense that there's a single formality such that when you evaluate things, when you evaluate a certain kind of an integral called the Riemann-Stieltjes integral, if the random variable happens to be discrete, then the evaluation gives you this. And if the random variable happens to be continuous, then the evaluation gives you this. And in fact, there's an intermediate case, which is called a mixed random variable, which we won't worry about. It just complicates the notation, but it's a mixture of the two. And maybe we'll see that later in the course when one arises naturally. Okay, so I'm going to do example. Let me call the example the case where the random variable x is uniform between 0 and 1. And of course, this is, in fact, it's already done somewhat in homework 0, and it's in the book, page 47 to 249. So this is the example that I took for the purpose of showing why we need to consider density functions. So the model is that we have this dial which picks out numbers along the circumference of the circle, and in this case the circumference of the circle is 1 and all the numbers between 0 and 1 are there. Or equivalently, we pick out a number at random in the interval between 0 and 1 in such a way that all numbers are equally likely, whatever that means. And we argue that what that means is that the distribution function should look like this. Okay, so this is the way we derived, this was a model for this idea. So here is the distribution function, which is the probability that x is less than or equal to t. Here's t. In this case, the values of the random variable all lie between 0 and 1. And here's the value 1. Because we know that with a distribution function, since the distribution function itself is a probability, that its values all lie between 0 and 1. And then we made the argument that if we do the graph, it would look like this. And its formula would be distribution function evaluated at t is equal to 0 if t is negative, 1 if t is greater than 1, and t for t between 0 and 1. Now, we derived this on a model. This is the graph of it. Actually, what we did is we derived the graph, and then from the graph we wrote down its formula. And the argument we made was that, well, it should be true that, first of all, for any t that's negative, the probability that x is less than that is 0 because it always lies between 0 and 1. And for any t that's greater than 1, the probability that t is less, or that x is less than that must be 1 because it always lies between 0 and 1. But in between, you could see that as x gets bigger, the probability that x is less than that is proportional to the value of t. In other words, when if I set here the value of t equal to 1/2, then the fraction of time, or the probability that when I spin this dial I would get a value less than 1/2 should be 1/2. because if all the points are equally likely, then the fraction of time of less than any t should be the ratio of the length of that interval to the length of the total interval. And the total interval, in this case, is length 1. So if that's t, then the ratio will be t over 1 or t. And that's exactly what this line represents. And so that's our distribution function. And distribution function always has the property that its value at minus infinity is 0, its value at plus infinity is 1, and it's non-decreasing. It can never oscillate. So as you move from left to right, it can either stay the same or increase, but it can never decrease. Every distribution function has that property, and this is the particular one for the so-called uniform random variable. And this is conventional notation here. The U stands for uniform. Uniform meaning that if I conducted this experiment lots of times, every time I spun this dial I would get a value. And that if I did it a zillion times, you would expect that these values would give me a uniform shade of gray. That they wouldn't tend to concentrate in one place or another place, because all points are supposed to be equally likely. Although the probability at any specific point is 0, because after all, if they're all equally likely, and their probabilities have to sum to 1, then if they would equal any non-zero number, and I added up an infinite number of non-zero numbers, then of course, equal numbers, then of course I couldn't get a finite value. So in order to make it finite, I have to have each of these have infinitesimal value, or 0. But when I integrate, when I add them up by integrating, I'm adding up an infinite number of infinitesimal values, and then the integral, in effect, gives me the area, which is not a positive number. Okay, so this is a distribution function. Now, what's the density function? Now, according to what we wrote here, from the fundamental theorem of calculus, if the integral of the density function is a distribution function, then the density function must be the derivative of the distribution function. So let me do that. So here is little f. Now, if I differentiate this, when I differentiate this branch, that is, I differentiate to 0, so here is little f, derivative of this function for every t that's negative is a derivative of this straight line, this flat line, a constant, so of course it's 0. So little f is 0 if t is negative. Similarly, if I differentiate this function for t that's greater than 1, I'm taking the slope of this line right here. Since that's constant, its slope is 0. The derivative of 1 is 0. There it is. So this is 0 for t greater than 1. And now, in between this region, the slope here is constant. In fact, the slope is exactly 1. And so the graph would look like this. So there's the density function. Density function has the property that it's never negative and that its total area is 1, which is obviously true in this case. So this graph is the derivative of this graph. But similarly, this graph is the integral of this graph. Because, for example, if I were to rename this, let me call this value u, and then make this independent, this argument here u, and then pick a value t, then for any value t right here, the value of this graph is the area to the left of t in the graph below it. So as my t moves from left to right, this graph traces the cumulative area. So here's my t moving from left to right down here, and here is the cumulative area, which is 0, then it grows linearly, then it reaches 1 and stays the same. Okay, so in other words, big F is the integral, maybe I should write it here, big F is equal to the integral from minus infinity to t of little f, and equal to the derivative of big F. This is always true, at least if the random variable is continuous. And this is just a special case, which you can see works in this case. Of course, it must always work. And the reason that if this is true, and conversely, this is the fundamental theorem of calculus. This is also sometimes called, going in the other direction, Leibniz's theorem, a Leibniz rule. In other words, if I simply take the derivative of this, then, that is, I calculate that, then when I differentiate the right-hand side, using the rule by which you differentiate an integral with respect to the upper limit, if you follow that, all that happens in effect is that the differential operator, in a sense, cancels out the integral operator, and this t comes down there and becomes the argument, and so when I differentiate that, I get that. So, if you tell me little f, I can get big F by integrating. If you tell me big F, I can get little f by differentiating. They're equivalent. So suppose I wanted to calculate something. For example, suppose I asked this. Suppose I said, what's the probability that x lies between 0.6 and 2.7? Now notice I didn't put the equal signs in here because remember it doesn't matter. Because in fact when I'm calculating a probability, what I'm doing is I'm simply adding up. What I'm doing here, when I'm calculating a probability, I'm simply adding up these guys, and when I take the integral at a point, that's just an infinitesimal amount or zero. So it doesn't matter whether I put the equal signs in there or not, because the probability that x equals any specific point is zero, unless the random variable is discrete, and then it may have a positive probability. Okay, so if it's continuous, the probability of equaling any specific value is zero, no matter what the density function is. Okay, now what is this probability? Well, we can do this various ways. First, let me calculate it by saying that's equal to the distribution function of x evaluated at 2.7 minus the distribution function of x evaluated at 0.6. That's what the formula says. This is A, that's B. What's capital F of 2.7? Well, if I go over here to the formula, I find that if t is greater than 1, which 2.7 is, then f of that is equal to 1. Okay, so f of 2.7 in this case is 1. This is formally the probability that x is less than or equal to 2.7, which happens 100% of the time in this model. What's capital F of 0.6? Well, since 0.6 lies between 0 and 1, I use this branch. Capital F of 0.6 is 0.6, so the answer is 0.6. When I subtract them, of course, I get 0.4. Okay, now I also could have said that the probability that x lies between 0.6 and 2.7 is the integral between 0.6 and 2.7 of the density function evaluated at t dt. Of course, when I evaluate this density function, what I'm doing is, if I can integrate it, I take the distribution function evaluated at 2.7, there it is, the distribution function evaluated at 0.6, there it is, and subtract them. But I could also have looked at it this way. I could have said, well, what is this? Here's my density function right here. So here is f of t, little f. Here's t. Here's the density function. It's this box. And I want to find the area under this curve between 0.6 and 2.7. So that's the area I want to find, which obviously is that amount right there. So the way I would do it is I could write this, or as being overly formal, I could write this as the integral from 0.6 to 1, that's this amount here, and in that region the density function has the value 1, plus the integral from 1 to 2.7, In that region, the density function has the value 0. This part is 0. This will give me exactly that. So, of course, I get the same answer no matter how I do it. Okay? So this is all really simple-minded. All you have to do is just follow the rules. Now, in any particular case, it may be hard to evaluate the integral depending on what the function is. But in our case, the function is always going to be easy because our point is not to come up with tricky integrals. The point is to look at things that make sense in practical applications. So the only things we're going to have to integrate are going to be things like constants or simple exponentials or easy powers, polynomials, t squared, t cubed, things like that. So this is easy. And the point is to understand what these relations are. Okay, any questions about that? Okay, so now I want to step back and go to another topic, which is called expected value. And then I'm going to evaluate expected values for discrete random variable and continuous random variable. And then once we get those concepts done, then I'm going to start looking at specific models of continuous random variables, such as the uniform, which is the first one, and a lot of the work is done already on that in homework 0, and then the exponential, which is another one of interest in a real model of reality. Okay, so can I erase this? It's very important to make sure you use the notation correctly now. Don't get mixed up between U and T. If there's a D something, don't write this. Right? That doesn't really make any sense. Okay? You have to put tell me the variable with respect to which I'm integrating. Because if I leave that out, if I'm integrating with respect to some other variable, then that thing is a constant. Now, it's easy to do this in freshman calculus because the problems are all so stupid that, in fact, you don't have to follow the rules. You just do it in your head, and then you look up the answer in the back of the book, and if it checks, you go on to the next problem. But you're missing the point there. It's just like saying, if I ask you to write a program to add up a couple of numbers, if you wrote the program incorrectly by leaving out a comma or something of that sort, it's not going to work. The fact that you don't have to run the program and could add up the numbers in your head, check in the back of the book, doesn't matter. You have to follow the rules because otherwise your programs aren't going to work for more complicated questions, the ones that you really need a computer for. Well, the same thing is true here. If you don't follow the rules, then when you tell your calculator to evaluate something, or you try and derive one of these results for something that's not a really stupid, simple-minded question, if you don't follow the rules, then the mathematics is not going to give you the right answer. So, very important. As I think you saw when you did the convolution problem, although you still don't know why you were doing convolution, but we're leading to that. Okay, so where I am now is I want to talk about what's in section 4.4, expected value, which is on page 150. So, this is section 4.4, page 150, expected value. First note that in the author's treatment, he talks about expected values, he says expectations of discrete random variables. But I don't want to restrict myself to discrete random variables. I want to be able to consider all random variables. Because as I keep on repeating, the concept is the same, whether the random variables are discrete or continuous. So, first of all, I always say first of all. By now I'm on nth of all. Okay, nth of all, this is a bad name, but it's one that's grown up through a convention and tradition. So I'll explain why it's bad, but it means average. So suppose I had some data. So give me some, somebody give me some numbers. Give me some numbers. Any numbers? 23. Okay, give me another one. 16. 2.7. 4. 8. I want to put 2.7 in there twice, or put something in there twice. Okay, so this is data. And suppose I wanted to calculate the average, which is often called x bar. Okay, so what I would do is I would take the values, which in this case are 23, and 16, and 2.7, and 4, and 2.7, add them up, and divide by the number of numbers, which is 1, 2, 3, 4, 5. So whatever that turns out to be, that would be the answer. But I could rewrite this like this. I could say that's equal to 23 times 1/5 plus 16 times 1/5. Okay, the reason it's 1/5 is that there's a denominator of 5 in each case. So there's the 23 over 5, here's 16 over 5, then I'm going to have 2.7 over 5. But I notice that the 2.7 is going to have a 1 over 5 here plus a 1 over 5 here. There are two of them. So the 2.7 is multiplied by 2/5, and then I have the 4, which is 1/5. And now you can go back and you could say, well, what do I have here? What I have is the values that the experiment gave me. In other words, the 23, the 16, the 2.7, and the 4 are the values that the random variable took when I performed the experiment. And each of them is multiplied by the fraction of time that it occurred during the experiment. In other words, the 23 occurred 1/5 of the time, the 16 1/5 of the time, the 2.7 2/5 of the time, and the 4 1/5 of the time. So another way to look at it is to say, well, this is equal to the sum of the values that the random variable takes times the probability that it takes those values. Because remember that in our model, one of our interpretations is that frequencies and probabilities are the same. So, for this reason, I'm going to define the expected value as follows. So you have to be convinced, later you will be convinced, that average is an important quantity. But this is sometimes called the expected value, written E of x. So this is expected value. That's one name. Another is expectation. Another is mean, or mean value, M-E-A-N. So I'll write down mean value. And the definition of it is that I take the values the random variable takes, which if it's discrete, I call T1, T2, and so forth. And then I weight the values that the random variable takes, in this case the 23, the 16, and so forth, by the probability that it takes that value, and I add it up over all possible values. So this is the definition of expectation. So it's the model. So expected value is the mathematical model of the notion of average. Okay, so if I have a random variable and I tell you its probability mass function, that means I tell you the values the random variable takes and the probability that it takes those values, then I can calculate from that this thing which is called the expected value, which will turn out to be equivalent to the long-run average. In other words, if I actually took data and did this experiment many times, then the average value that I would compute, and we're going to see this soon when we do some simulation, the average value that I would get would be approximately equal to the expected value that I would calculate. And in fact, in principle, if I ran this experiment to infinity, if I took an infinite number of samples, then the theoretical expected value and the observed average would be the same. In principle, of course, you can't really do that. That's part of the difficulty with this course. All right, so this is easy now. In any particular case, you give me the probability mass function, I can calculate the expected value. All right, so let me do that for a couple of simple examples. And let's see, these are probably in the book. Okay, first of all, this statement right here, where I'm defining E of x. In the book on page 151, the author says that E of x is equal to the sum of x times little p of x over all x element of A. Well, this and this is the same thing. He just uses different notation. So he uses these x's. He's adding up. Here he's trying to, I think he's trying to indicate, although it's kind of not clear, that this x doesn't have to be countable because the same thing sort of will occur in the continuous case, except we're not going to have sum, we'll have an integral. So I'm just saying that this is in the book, and this really means the same thing as that, but my advice is to use this. This is a much more meaningful notation, I think, unless you like to think in strict mathematical formalities. Okay, so here are my examples. First one is die. Okay, so let's do some examples. Of course, as usual, these examples are all going to give me answers that I knew what the answer was anyhow. Okay, so example 1. X equals the face value of a fair die. Okay, so what is the expected value of X? Well, I take the values the random variable takes, which in this case are the numbers 1 through 6. So we have 1, 2, 3, 4, 5, and 6. And I multiply or weight each value the random variable takes by the probability that it takes that number, and I add them up. In this case, they're all 1/6 because it's a fair die by definition. And so what I have here then is 1 plus 2 and so forth up through 6 divided by 6. So the sum of these numbers is, what's that, 21? So it's going to be 21 over 6, which is 3.5. Okay, so this says that if I were to roll the die over and over again and calculate the average value that I got, in the long run that average value would convert to the number 3.5. So the first thing to recognize is that this 3.5 is kind of a central value or mean value. It's sort of in the middle. In fact, in this particular case, if I just took the lowest value and the highest value and added them up and divided by 2 to get the one in the middle, I would get 7 over 2, or 3.5. Of course, this doesn't always work. It works in this case because in this case the probabilities are all equally likely. So this thing just picks a number that's actually the center of mass or center of gravity. You might recognize this from physics. This formula is exactly the same as the formula for finding the center of gravity. And this says that if I have these values that lie between 1 and 6 and they spread out evenly, the center of gravity is right in the middle, 3.5. Notice also that 3.5 is not one of the values that the random variable can take. The random variable in this case can only take the values 1, 2, 3, 4, 5, 6. So to say that it is the expected value is really a misleading term, because in some sense, if I had to come up with a single value that most represents the, most summarizes the data, as we'll see later, and as I think everybody intuitively knows, if you had to pick one value that sort of summarizes everything, the central value or this center of mass value or the expected value is defined here, or the mean value, is the most reasonable thing. However, it doesn't necessarily represent a value that the random variable can ever take. So to say that it's the one that's expected doesn't make any sense, because you would never expect this random variable to have the value 3.5, because it can never take the value 3.5. It can only take the integer values 1 through 6. So that's the first thing. That's why I say that this terminology, which has grown up through historically, is not really the best terminology. I would like to use mean value, but everybody uses mean value and expected value and that notation interchangeably. Okay, let's look at example 2. example 2 is, now we're going to let x equal the value of a roll of 2 fair dice. So again, we're going to calculate the expected value by taking the values the random variable takes multiplied by the probability that it takes them. Remember that this thing here is simply writing out exactly what this indicates. So I know that a lot of people have trouble with this, but I don't know why. Because in any particular case, all you have to do is ask what values the random variable takes, what the probability is it takes them, and then add them, multiply them together and add them up. So it's really simple. Okay, so I'm going to roll 2 fair dice here. So what are the values you can take? Well, the lowest value you can get is 2, and the probability of that is 1 over 36. The next value you can get is 3, and the probability of that is 2 over 36. And then you can get the value 4, and its probability is 3 over 36, and so on. And the last value is 12, and the probability of that is 1 over 36. So now you just do that arithmetic, and it'll turn out that the answer is exactly equal to 7. So in this case, the value that is the expected value, which is a 7, is actually a value that the random variable can take, because it can take the values, integers, between 2 and 12. However, that just happens this way, but as this example shows you, it's not necessary, because a single die can never take the value 3.5. Okay, now, note, let me put it in parentheses here, that's equal to 3.5 plus 3.5. In other words, if I roll 2 dice, the expected value of the sum of the 2 dice is equal to the sum of the expected values of the individual dice. So is that a coincidence? Of course not. The sum of the average is equal to the average of the sums. So, let me write that down. So this is a theorem. Very useful theorem. So let's see. It's in the book. Here's what I want to write down. Suppose that x, some random variable, can be viewed as the sum, x1 plus x2, and so forth. I'll say xn. So in our particular case, this is the sum of 2 dice, but it could be any number of dice. And then the theorem says, it says that the expected value of the sum is equal to the sum of the expected values. Now this is a corollary to another theorem that's given on page 368. So the point that I'm making by saying this is, in one sense, this is intuitively obvious. Obviously, if I'm going to add up random variables, it ought to be true that the average value of the sum is the sum of the averages. So once you see this, you should believe it. However, the fact that it's a corollary to a bigger theorem and it's not listed until you get to page 368 indicates the difficulty of proving this. Because in order to prove that this is true, I would have to be able to calculate the expected value of the random variable x, which represents this sum in general. And how do I do that? Well, we don't know how to do that. And in fact, that's part of what convolution is about. If I add up random variables, then the description of the new random variable, that's their sum, is a complicated function of the descriptions of the random variables that make up the sum. And so to prove mathematically that the expected value of the sum is the sum of the expected values, no matter what the random variables are, is a big deal. And in fact, this is true whether the random variables are discrete or continuous. So again, we're not going to prove this stuff because there's, in some sense, unless you're interested in mathematics for its own sake, there's no point proving, no necessity to prove something that is obviously true. The only time you want to prove something is when it turns out to be counter to your intuition. That's when you need mathematics. But if you think it's true, then what's the big deal if it turns out to be true? It's only a big deal if you think it's true if it turns out to be false, or vice versa. All right, so we're going to see this also shortly in the course when things start to speed up, because what I'm going to be doing now is I'm going to be giving examples and proving these things in some cases, and then simulating them, and you'll run a simulation, which you don't know how to do yet, and you'll compare the theory with the simulation experiment, and of course it'll always work. Okay. So let me write down the general formula then for expected value. So here's my expected value. And I'm going to write it in two ways. Well, I'm going to write two different versions of it. Because remember that we have discrete and continuous random variables. The author treats them separately, but as I keep on emphasizing, they're the same thing. So if the random variable is discrete, what I do is I take the values the random variable takes, which I'm calling T1, T2, and so forth. I weight the value by the probability that it takes that value, and then I add it up over all possible values. Okay, that's if the random variable is discrete. So what if it's continuous? Would have an expected value also. So what formula should I use for the expected value of a continuous random variable? Well, now the values that the random variable takes, instead of calling them T1, T2, and so forth, they're not countable, so I'll just call them T. And they're going to range over all values that the random variable can take, which is a continuum, not just a countable discrete set. And what is the probability that a continuous random variable takes the value T? Well, for any particular value, the probability that a continuous random variable takes that value is 0. But what we want to do is we want to add up an infinite number of those infinitesimal zeros. So I replaced, just as I indicated before, I replaced the probability mass function by the density function, dt. So this piece right here, this is the width, this is the area of that infinitesimal strip. This represents the probability that x lies between t and t plus dt. This is the value the random variable takes, and then I add up this uncountably infinite number of them, which means I integrate this over all possible values of t, which means I go from minus to plus infinity. So this is the continuous case. Okay, this is in the book. Let's see, he defines it on page 234. But you don't want to wait 100 pages to get there, because it's obvious that these things are the same. I think it's obvious. That's what I keep on saying. That's what you have to say. You have to convince yourself at the end. It doesn't matter whether you're talking about discrete or continuous, the concept is the same. And the way I understand this is I interpret the density function dt, which is the area of this infinitesimal strip, as the probability that x actually takes the value t. But now instead of adding them up over a countable number, what I'm doing is this. I have this density function. There it is. And I'm going to take the value, the probability that it takes any particular value, which is that, and I'm going to weight it by the value t, and I'm going to add them up between minus and plus infinity. Okay, so let's do an example. So here's example 3. Suppose that x is uniform, 0, 1. This is the only one that we know so far. Well, remember there's an infinite number of continuous random variables, just like there's an infinite number of discrete random variables. But this is the simplest one, and arguably the most important one, right at the beginning. Okay, so the question is, what's the expected value of x? In other words, if I'm going to spin this dial, and this is 0 and this is 1, so I'm going to pick out a number at random in the interval between 0 and 1. On average, what number am I going to get? According to the formula, the formula right here, it would be the integral from minus to plus infinity, I'm just recopying it, of the value the random variable takes times its density function. But what is the density function? Well, the density function for this thing is just this box. 0, 1, 1, t, little f of t. And remember, I keep on stressing the most important thing in this course is not confusing little f with big F. Okay, so you've got to remember uppercase, lowercase. So this is the formula right here. Okay, so little f, though, is going to be 0, except when t lies between 0 and 1. So I can immediately rewrite this as the integral from 0 to 1 of t times 1 et. Because between minus infinity and 0, the little f is 0, not 1. And between 1 and plus infinity, the little f is 0, not 1. So the expected value is given by this. Okay, now comes the fundamental theorem of calculus. The integrand is t, so I find the function whose derivative is t, which is obviously t squared over 2. If I differentiate t squared over 2 with respect to t, I get t. And then I plug in the upper limit, the lower limit, and subtract them. Because when I plug in the upper limit, I get 1/2. When I plug in the lower limit, I get 0. The answer is 1/2. But of course, that's the expected value. That's what everybody knows. That's what you would guess. Because if I'm picking out a number in the interval between 0 and 1 in a uniform fashion, meaning the probability spread out evenly here, then just like with the single die, where the value comes out to between in the middle, between 1 and 6, which is 3.5, it's going to come out in the middle, which is 1/2. So this example shows you that the expected value is exactly what you would expect. And another way to look at it is that if I spin this dial and take data, then every time I do it, I'm going to get a value that's going to lie someplace between 0 and 1. And the values are going to tend to spread out evenly. And so you can see that on average, the values to the left of 1/2 are going to, in a sense, balance the values to the right, and everything is going to average out to its center of gravity, which is right in the middle, which is 1/2. So this shows you that this definition gives, at least in a simple case, exactly what it must. But of course you know that, because once you understand this, you see this is the same as this, and this is simply our model of average. So it all makes perfect sense, as I say over and over again. Okay, so any questions about that? So now in any case, if I gave you a random variable, I would have to define it somehow, and if it was discrete, then I could give you its probability mass function and ask you to calculate the expected value. If it's continuous, I could give you the density function. Of course, if I gave you the distribution function, then if it's discrete, you could calculate the probability mass function from the distribution function. Of course, why would you have to do that? I mean, why would I express this in terms of its distribution function? Just to be annoying, because the discrete case, you want to work directly with the probability mass function. But if the random variable is continuous, if I give you a distribution function, then you have to differentiate that to get the density function. That's where this thing comes from. And then I plug that into the formula, and then I just do the arithmetic. But the arithmetic is as simple or as difficult as this function is complicated. And whether this function is complicated or not is irrelevant in terms of its application. The important thing is that in freshman calculus, these functions are usually defined to be a single formula everywhere, whereas in these applications, these functions tend to be given by some formula, which has different branches depending on whether t lies in some range or some other range or some other range. That's the difficulty. Okay, so let me give another example now. And this is actually homework 2. Okay, so now You can go to homework 2. You can download it from the course website. Homework 2, and it is the birthday problem continued. So, if I'm going to ask you to calculate the expected value for a discrete random variable, in one sense, it's too simple to do, worry about, because all you're doing is plugging into this formula. So what I want to do is I want to look at the birthday problem, in which case the concept is the same, but it's more difficult to use this formula at first glance because there's lots of terms here, and these probabilities are not obvious numbers like 1/6 or 1/2 or something like that. So remember what the question was. In homework 1, so this is a continuation of homework 1. So in homework 1, what you did was you simulated the idea in which you went around to people and you asked them one at a time what their birthday was, and then you did that until you got 2 people with the same birthday. That was a match. And then you said, how many people was that? And what you did is you did this experiment, I guess it was 10,000 times, and each time you did it, you observed how many people it took. And that number could be anywhere from 2 to 366. And then you kept a running average of those values, and you saw that as the number of experiments got larger and larger, the average tended to converge. It stabilized, and it stabilized at a value which was somewhere between 24 and 25, which for many people is an intuitively surprising result, because it's a much smaller number than most people would expect. So what we already have is we've already got a case where we have simulated an experiment, and we found that the long-run average is roughly 24.5, someplace between 24 and 25. And so now the question is, the homework problem is to actually calculate, plug into this formula, and see what value you get. This will give you the theoretical expected value, which is the theoretical idealization of the notion of average, which it'll turn out will be a number between 24 and 25, except that now everybody should get exactly the same answer because there's one specific expected value, one theoretical value. Okay, so this is the problem, and so what you're doing here now is you're going to calculate this expected value, and what it is it's the values the random variable takes, which in our case are integers, because every time I run the experiment, the value of the random variable, the number of people I question, is either 2, 3, 4, 5, and so forth. So in other words, I'm going to take the integer values multiplied by the probability that in fact that is the number of people you question, summed over all possible values, which is between 2 and 366. So you can't do this problem by hand, it's not practical. So what I have to do is I have to figure out what these probabilities are. I got to put them in this formula, and I got to evaluate it. And to figure out what the probabilities are, part of my point here is that, as often is the case in probability, the way to do things is to do things recursively. So I'm going to show you how to calculate these probabilities recursively so that this is then a simple programming problem. You can do it in about, I don't know, that much space. And then run in an instant, and it'll give you the exact correct answer. So the question is, what are the probabilities? Okay, so let me start with this. I won't have time to finish it, but I'll do this next time. And once you see it, this problem, if you know how to write a program, which of course everybody's supposed to, that's one of the prerequisites for the course, even I could do this. I could do this in BASIC, because that's about all I know, and it still only takes that big. Okay, so what is the expected value? First, I got to calculate the probabilities. So what's the probability that x equals 2? In other words, what's the probability that when I question people one at a time, the first match will come on the second person? As we all know, that value is 1 over 365. The reason being that when you question the first person, no matter what birthday he has, the second person has one chance out of 365 of having the same birthday. So that's the probability of a match. So when j is equal to 2, this value here is, this is 2, that value is 1 over 365. Okay, what about 3? So here is the probability that x equals 3. In other words, that the first match occurs on the third person. So let me write it like this. For reasons that are going to become obvious shortly, I'm going to rewrite this as 365 over 365 times 1 over 365. Of course, that 365 over 365 is just the value 1, doesn't mean anything. All right, now what's the probability that x equals 3? I'm going to write it this way. First, let me write it, and then I'll explain it. It's 365 over 365, which is 1, times 364 over 365 times 2 over 365. Okay, so let me interpret this. One way of interpreting this is to say, I'm going to define my sample space as follows. What I'm going to do is, in the denominator, I'm going to ask how many different ways I can get birthdays for 3 people. And the answer is, there are 365 choices for the birthday of the first person, 365 choices for the birthday of the second, 365 choices for the birthday of the third. This is the stuff we did at the beginning of the course. So 365 cubed represents a number of different possible birthdays, 3 tuples I can get, and if I consider every possible 3 tuple equally likely, then the probability that I will get my first match on the third person has in the numerator the number of ways that can happen. And there are 365 choices for the first person, but if the second person is not to match, there are 364 choices for him, and if the third person is to match one of the first 2, he must choose, he has 2 possibilities, namely whatever the first 2 birthdays were out of 365. Another way to look at this is to look at this as product of conditional probabilities. This value is just 1. This is the probability the second person's birthday does not match the first. This is the probability the second person's birthday matches one of the first 2, given that the first 2 did not match. Okay, let me write the next term, and you can see what's going on here. It becomes sort of obvious. What's the probability that the first match will occur on the fourth person? So this is the probability that the first person's birthday doesn't match anybody previous. Can't. That's 1. Then 364 over 365 is the probability that the second person's birthday does not match the first. Then 363 over 365 is the probability that the third person's birthday does not match either of the first 2. And then 3 over 365 is the probability that the fourth person's birthday matches one of the first 3. So you can immediately see what the pattern is. So in fact, in general, I can write this. What's the probability that x is equal to j? And the answer is, well, it's 365 over 365, and so forth. And then the next to the last term is 365 minus j plus 2 divided by 365. And then the last term is j minus 1 divided by 365. So what you need to do is you need to convince yourself that this is the general representation of each of these. That is, when j is equal to 4, then 365 minus 4 plus 2 would be 365 minus 2, which is 363. And then the last term would be 4 minus 1 over 365. That would be 3 over 365. So you can see that if you were to write all of these out between 2 and 366, the jth one would be exactly in this form. And so the trick now is to write a program that will calculate these guys But you don't want to calculate these guys directly from this, because this is going to give you a gigantic numerator, a gigantic denominator, a gigantic numerator, or maybe a small numerator, I don't know. But if you calculate this directly, you're going to run into big numerical problems. So what you want to do is here's the general strategy. I'm going to calculate the probability of xj, x equaling j, in terms of, I'll just write a squiggle there, the probability that x is equal to j minus 1. So I'll do this in class next time. So I'll leave this for you to think about. But once I have this recursion, then all I do is calculate. I have a starting point. I calculate the first one, which is easy, and then I use the recursion so that at each step I calculate the probability for one term in terms of the probability for the previous term. And I weight it by the value of j, I accumulate them, and the result is my answer. So let me leave it like this. Right now I'm going to leave it like this. On Thursday, I'll write the next step, because once I do that, there's really nothing left except to put it in code. And then let's make this due a week from today so you can work on it over the weekend. But once I write this next step, it takes a minute. And, but I want to illustrate these points. The points being that a way to calculate these things, you want to calculate the probabilities, is you want to be clever. You want to use stuff you learned in analysis of algorithms, otherwise things aren't going to work. And the second thing is that this will give a check of the comparison with theory and experiment for the first time using simulation. And it'll turn out to be exactly what you expect it to be. Okay, any questions about this? Okay, so download this, have this in front of you next time, and I'll finish it.